Thank you for being here. Seriously, this has been one of the best conferences I have been. So thank you to the organizers and thank you to the speakers for making it such a good conference. Now it's downhill. So I'm going to start from a website. This graphic you've seen so many times, but I don't know how many people know that you can go to a website and actually control this graphic. So I'm going to start from this. So you can actually sort it in different ways by date, different ways for electromagnetic. You can toggle different things. You can change the points. You can change the sizes, etc. So if you didn't know that, I should have a QR code up here, but if you just Google masses graveyard LIGO, you're going to find it. Okay?
On that note, then I have a question. Can you change the colors of the black holes that are forming from the two black holes that are merging so they don't mix together?
I don't think you can change the colors, but you're taking time away from my... Yeah, so honestly, I don't know that we can go beyond this with this graphic. Okay. We need new ideas, so I think this may be the last time you see it. Okay, all right, now we're gonna go to the top. And let's see if we can do that, and that. Now let's see if the gadget is working. What did I do with it? You have it. Okay. All right, so I'm gonna try and sort of bring together a few different ideas and results that are coming out of the group at Northwestern on black hole masses and spins. Most of what I'm gonna present is unpublished actually. And we're still processing and understanding the results. Now, Ilya asked that question that he asked a little bit before, so I had to change my whole talk and make it non-parametric. So, in the past hour. No, of course not. Most of the work is going to be non-parametric analysis. As we close the conference, I'm going to go back to the ground truth, the data, and I'm going to tell you about mass peaks and bumps and other things that we may or may not believe. Certainly, Ilya doesn't. We're going to find out that spins care about masses, and we're going to find out that the world is three-dimensional. But also, we are going to find out that models for the data do make a difference and sometimes mess things up, so we need to be mindful. And then there will be insertions of astrophysical models, but I'm not going to explain anything about the models. So if you want to know more about Poseidon and how it works, you'll have to come and visit Northwestern. All right, let's start from the masses. This is the collaborations mass distribution, our latest results. And you heard from Aditya at the opening of the conference, who led the populations paper for the whole collaboration. And we have, let's see if this works actually. We have a clear peak at, we call it the 10 solar mass peak. I'm going to give you the ranges within the error bars with the different data models. So I think sometimes this is important to keep in mind. This is a narrow peak. This is a strong peak, 9 to 11 solar masses. For individual masses, this is very narrow, a strong statement. We have a bump, the 35 solar mass bump is actually constrained within 29 and 36. And then we have something or nothing at about 20 solar masses, and maybe even less of a something at around 60 solar masses. Let me see if the laser thing works. So, you know, maybe one of the models shows something there as a little bump. Now, we're going to look at it, same data, but modeled non-parametrically. So this is work and some more that I present that was led by a student at Northwestern, Omkar Sridhar, and Anarya Ray, a postdoc that many of you know. And here's how the same data look if we analyze them with bin Gaussian processes. It's not nice, okay? The press wouldn't pick that up. It looks ugly and messy and not very serious. However, there's a clear peak. Okay, so even with non-parametric analysis, some results are absolutely there. So basically you're fitting histograms, simply told, okay? They're not completely independent, but you're fitting histograms. And the error bars are bigger because you don't have a sort of prescribed functional model. But the 10 solar mass peak is there. And these are the red line, and the 35 solar mass peak maybe is there, but you can see it's weaker. So in non-parametric, you don't see, you wouldn't identify it as a peak here. You would say, oh, there's something here, and maybe there's an extra peak at 20 solar masses. But you wouldn't claim this if you didn't have the other modeling, okay? You would only claim the 10 solar masses. So I want to emphasize this. And then there's a 20 solar mass, a kind of a hint. And, you know, is there a bump at 60? I don't know. Maybe when I'm dreaming. All right, so what have people, now these features, they're not the first time, especially with the non-parametric models, they're not the first time that they have appeared in our data. So people have written about the origins of these features. So just trying to be very concise, and probably I'm missing references, so apologies already. But I think we only have one explanation for the 10 solar mass peak. Is Licky already gone? No, Licky is there. Isolated binary stable mass transfer, that's been around for a while. And then the mid-30s crisis, Roy and collaborators have concluded that we're in crisis, because basically I think in some ways they excluded all the explanations that have been around. And we're going to work on this one through the talk. But also we're going to work on the 10 solar mass peak. But we're going to do this now, as other people have done in the past, in conjunction with spin properties. We're going to do it for different mass ranges, and we're going to bring in mass ratios. And mass ratios have been ignored for a while, partly because they're even harder to measure. So let's see what we can do. So I'm going to start with a couple of questions. Could it be that the 10 solar mass peak be due to dynamical processes? And how can we resolve or get out of the mid-30s crisis? All right, so as I said, Licky-Vanson, 2022. I'm going too fast here. This is not Licky's plot. This came up with a very clear explanation for what could be producing the 10 solar mass peak in connection to stable mass transfer. Latest results from our elaborate, Poseidon simulations led by Monica Gallegos-Garcia, what we're finding is that actually in our models now, and Monica was the one who said, common envelope doesn't matter. But it wasn't a whole population synthesis, that paper, okay, in 2021. What we're finding here is that there is a strong peak at 10 solar masses for both common envelope and stable mass transfer. This is one model you're looking at. And I'm not going to explain all the details for why, but basically, why do we have that edge at 10 solar masses for this model? Anything below gets merged, gets destroyed in mergers, common envelope, etc. So what we're finding now, and what we'll be arguing, but not very soon, because we're really still digging into the data, the simulation data, is that it may not be just stable mass transfer that's producing this. Then, could the dense solar mass peak be from dense clusters? Well, if you look at latest global cluster simulations, here's an example from Claire Yi and collaborators, including Maya and Kyle Kremer, who are here, or maybe some of them left. Look at this. If you look, this is logarithmic scale now. There's a strong peak up there, 10 solar masses. This is the red band is 9 to 11. Again, one model. And I won't go into describing all of this. So one could say, sure, you can explain the 10 solar mass peak from clusters, but only if you look at masses, only. Okay? So now, I thought I had that already, but only if you look at black hole masses. So now we're going to unpack things and look at two more dimensions. We're going to look at mass ratios and effective spins, and we're going to do it not for the whole population, because when we do it for the whole population, we're learning some things, but we're not getting to be able to address the questions I've raised and more. So back to the non-parametric modeling of the mass distribution. It's not looking very good, and the same peaks as before. Okay. We're gonna, what we did with Anaria is we're splitting the distribution in 3 mass bins or ranges, whatever you want to call it. Here they are, below 30 solar masses, 30 to 45 solar masses, and above 45 solar masses. Now look at it again. Below 30 solar masses, and you would ask, why below 30 solar masses? Nothing is going on significant below 30 solar masses here for this non-parametric model. Maybe at 45 something is happening, but you could stop at 35, and then this one. And I'll tell you that we are splitting these this way because when we looked at mass ratio distributions for many different bins and combinations, and at chi-effective distributions, it's these 3 groups that have different behavior in masses and chi-effective. So we're proposing that it's these roughly, of course, don't take it plus or minus 1 solar mass, that it's these 3 different ranges that are behaving differently in the other 2 dimensions, mass ratio and chi-effective. So, differently in what way? Let's look at mass ratios. I feel like I need to be looking more at the screen. Here's what we're finding. Let's call these the low mass black holes. For mass ratios, I'm showing you, again, non-parametric modeling, and we're not doing it separately in each dimension. The actual modeling is non-parametric in 3 dimensions. Okay? We're plotting it marginalized in dimensions. So we have a very significant peak at 0.6, 0.8. The black lines are the priors. My dotted line is not there. So it's really a peak. 0.6, 0.7, 6, 7, as my 13-year-old says. A few people know. I live with that every day. Also, now, this is not new. It has been seen before, but it's building a story. And it's now very strong in non-parametric modeling. 30 to 45, clearly different. Again, priors, trailing up to unity. Okay? Again, has been seen before with different ways, not with non-parametric models, okay? Including from the collaboration. But for this regime specifically that we're showing here, not necessarily for the same regimes, etc. Again, we're choosing them for both spin and mass ratios that you haven't seen yet. Now we're going to go above 45. And here, I would say we see nothing, because you see the priors. Okay? But it's the beginning of a hint. which could go away, that maybe there's a peak around 0.5. And in fact, the peak is just above 0.5. And I emphasize this for a reason. Because I'm the last talk of the conference, so I think I have license to speculate. Okay. But it's not statistically significant. In addition to that, also not statistically significant, but there is this potential peak at 0.1, 0.2, and that I don't know what to make of. Again, mass ratios, okay? Gravitational waves, it's not going back for me. Gravitational waves with 0.1, 0.2, if that thing is real, which I don't think it is, we will have real trouble. All right, now let's look at spins. All right, peak for the low masses at low but positive values. These bands are coming out of our own analysis. For the middle bin, clearly gets much narrower, okay, and shifts to the left. Almost symmetric at 0, but not symmetric at 0. And then for the last bin, nothing, okay, consistent with priors. So now I'm going to put them all together. And on top of them, there's red lines. And those red lines are cluster models. Older, from a compilation that Mike Zevin and collaborators have put. Look, I didn't remember the year and the archive, and I was going to look it up, but I forgot. Okay. So these models are coming from a public database. The different red lines correspond to different initial spins for the black holes. It does make a difference because of escape fractions, etc. And we're looking only at 1G, 1G. And what else do I need to say? And the priors are still there. And I would argue now that, Anaria and I would argue now that the low mass things are not coming from clusters, or at least they don't have a dominant contribution from clusters. In fact, we think the clusters are there, because if they were not there, the data would not have a significant component below 0. Is it significant? Is it not? One might argue. But we don't think that the contribution of clusters is non-zero, but certainly it's not dominant. The middle bin, we would argue this is really certainly major contribution from clusters, but potentially even dominated. Okay? I'll come back to that. And the high bin, we would say, maybe we have a measurement here. You can ignore these things and say, we don't have enough information with non-parametric models. Or you can look maybe at this one only, the mass ratio, and say the clusters clearly don't agree. Okay? All right. Now, newer cluster models from Claire Yi. And if you put everything together and you put not just the 1G mergers, but also hierarchical, here's what you're finding in the mass ratio distribution. Of course, a peak at 0.5, 2G, 1G. No surprise in the models. A peak at 0.5, which may or may not be there. The chi-effective, nothing. It's really in the prior. Okay? Now, even in the models, it's not centered at 0.5. It's just above 0.5. And the cluster people know why. Okay? It makes sense in the theory. Because you have a range of masses and the heavier go in the center. And I asked this question to Claire, and so she had to explain it to me. So I don't take credit for the explanation. It didn't come to my mind immediately. So that's why I emphasize the peak is to the right of a half. But the height of this peak varies with models. Depends on initial spins, and it depends on escape velocity for the cluster. So it may or may not be as pronounced in the data. Yep.
Why is it not like picking at 0.5 just because you lose some energy as you merge?
Claire, Carl, you go ahead, it's your work.
Yeah, pretty much. You lose 5–10% of the mass in Draper waves. So if everything's 20 solar mass in the merger, you get 38 plus 1.
So it's not 0.5.
Yeah, yeah. Okay. And this is consistent with prior, so we're not comparing to that. So I would say maybe the massive things are in agreement with a cluster contribution, some significant cluster contribution. Now, I'd like to go back to the mass ratios and now bring in astrophysical models of isolated binaries, okay? Because we were looking at clusters. So look at this width, 0.6 to 0.8, roughly. And I'm going to show you some isolated binary evolution models that we have now. Here's one model as an example. We haven't done the full statistical analysis of all our models, etc. And 0.5 to 0.7 at similar drop, statistical drop. One model. Collection of models. Sometimes the peak is elsewhere, clearly. Okay? But it could tell us something about these models. There are models who give you again and again 0.6 to 0.5, 0.7. And then okay, so I'll pause here. This is now, we've been focusing on mass ratios and chi-effective with clusters and field binaries, and this is below 30 solar masses. So remember what I said. Could the 10 solar mass peak be clusters? If you look at the masses only, yes. If you look at mass ratios and chi-effective, no. So we're back to 10 solar mass peak is isolated binaries. But we're finding that it's not only stable mass transfer at this point. So let's go back to primary black hole masses. And this is all theory because everybody can remember the 10 solar mass peak. This is the original model I showed you, which has not been handpicked. We haven't looked at all our models. And this is a collection of models where everything is the same except we change the supernova treatment, the core collapse treatment for the black hole mass, progenitor, and kicks. Okay? And what do you see? They all have a peak. This is total. I'm not separating in channels for the different models. They all have some peak. If you stare at this enough, we could quantify it, but I'm telling you, these are hot off the oven, okay? But you can see they all have some kind of a peak. But the location, the location and the width, how pronounced the width, the peak is not dictated by the channels. It's dictated by the prescription of the black hole's mass progenitor, especially. So we may have an opportunity for calibration with that sharp peak at 10 solar masses in the data. All right. I'm about to switch to a couple of tidbits that have come up from time to time, and I'm going to do them quickly from time to time at this conference. So where is the peri-instability supernova gap? Nobody doubts that process happens in stars, okay? So, of course, Maya, Eric Thrain with Hui Tong had the idea to look at the secondaries because the primaries are the massive ones where you expect the clusters to mess you up, and we're finding the more massive populations have strong contributions from the clusters. We're confirming in some ways, but we have additional pieces of evidence. Okay, so they looked at, I think that's a powerful way to look at things, and they were the first to do it. And you look at the secondary mass, so check the companions, and they have found what appears as an extremely strong gap. Now, data, what the data tell us does depend on what model we're using to fit. So I will now show you with different models what we're finding. It doesn't mean the gap is not there, but I would argue we're not certain it's there yet. It must be there, because that's where the gap will exist, in the secondary black hole masses. That's the key idea. So the models that were used had the structure of a gap and a prior for the width. That's my understanding what it did in the paper. So gap identified, 50 to 100 solar masses, and above 100 there is a rise. We're analyzing it not non-parametric. We can't find it. But we're analyzing it with a much less prescriptive model. We find a drop at around 50 solar masses, and then there could be a gap, but it's not required. This is not a gap. It just says the data can't tell you yet with this model. So possibly a gap above 60, which is more consistent with pair instability mass range. But it's not in the data yet. Again, a rise above 100 solar masses, clearly. So I would say, let's wait. Now, I have another more controversial thing, and may upset some people, but I'll do it. We looked with non-parametric analysis at Q-Chi effective. So is it there? This is the whole population. Let me do it again. The whole population, Q-Chi effective. You can throw calculations of quantitative measures, but we're not finding a correlation. Then we split it in the 3 mass ranges, and what we're finding is the low masses, basically, it's the peak at 0.6, 0.7, and it's the slightly positive chi effectives. And in the middle, trailing against 1, reaching all the way to 1, and narrow range closer to 0. And then in the very high regime, a high density at 0.5. But the chi effective, I don't know what to make of it. You saw the data earlier. Now we calculate the Pearson correlation coefficient for these data, for each bin and for the total bin. And they're all consistent with 0. So we're not finding a correlation. Okay. So, conclusions. You're happy. So what I would close with is potentially a coherent picture is coming together with some strong statements and some uncertain statements. I will not read them one by one. And the 10 solar mass peak, which is the strongest, we would argue, but this is astrophysical modeling purely, that it could be produced by both channels. And maybe the location and the sharpness could help us calibrate black hole supernova parameterization. It's still a parameterization. For the secondary masses, I just told you about that. Now, I said conclusions, but I can't resist. I hear Smadar's voice in my head. What about triples? But she's not here, so I don't have to do anything with triples. But what about the accretion efficiency that everybody has been asking about throughout the conference? So it affects many things. And all I want to do is tell you that with a postdoc who came from Tassos Fragos' group, he was a student there, we're developing a physically motivated method that goes back to Popham and Narayan from 91. But it's not identical. So we're basing the physics on that, and we're adapting it and modifying it. We are getting more contact binaries, but a lot of the binaries are getting to go through stable mass transfer, spin up, form BE stars in different types of configurations with the right mass distribution. We used to have we couldn't reproduce the mass distribution. And the accretion efficiencies we used to get with the MESA prescription is this, with 2 massive stars across periods and masses. And for the same grid, new prescription, we're getting this distribution of accretion efficiencies. And the paper will come out, okay? So I'm giving you punchlines and no explanation. Back to my conclusions, and I'll stop.
Hi, Vicky. This is Reed Essick from CETA. Thank you for the great talk. This is not just about the parent stability, but also the lower mass cap as well. I think there's an interesting sociological question of how people define the word gap. Because in the plots that you had, if you could flip back to the envelope plot.
Yeah, I was thinking about it during Amanda's talk.
Like the constraints that you find, there's still, I was actually, the model with Anaria, right?
There's a drop.
And it's at high confidence.
Yes,
right?
it is in both models. I
correct,
agree.
yeah. And so to me, gap really means
it's logarithmic,
dearth.
so it's a significant drop.
Yeah.
And I agree, I wouldn't even call it, I mean, you can call it semantics. It's a strong drop. And when I look at this plot, I don't see a gap. When I look at this plot, oh, I'm sorry, where am I going? Where is the other? Sorry. Too fast. When I look at this plot, that's a gap. That's a gap. That's a PISN gap.
So I guess, can you quantify what you would have to see before you would say gap? Do you actually have to see 0 rates? Or is it 1 order of magnitude, 2 orders of magnitude?
With data, there is no 0 rates. It's always an upper limit. But it's a nuanced discussion. But I would expect the power law going from that to almost vertical.
The gap would be the sharpness of the roll off.
Yes. Cool. Thank you. Yeah. But I agree. It is, one can argue. Yeah.
Yeah, just to add a data point to that before asking my real question. So in Hui's paper, he tried also like a notch filter model, which looks a lot more similar to Anaria in your result. And the finding is a base factor of...
No, our model does not, I mean, the notch filter doesn't look like our model.
It's
a broken power law.
No, the notch, in the appendix, there's a notch filter model which basically allows the gap to be arbitrarily filled in.
Okay.
And so so a sharp gap is preferred to no gap, that's like the maximum likelihood model we found, and that's preferred with a Bayes factor of like 80 to 90. So it's like 90 times more likely for there to be a gap, which of course is not like, it's just a statistical statement.
We calculated Bayes factors. It's not that big of a difference. But again, it's introduced. We've had these discussions before. There was another gap of low mass black holes that we were arguing. Also, the paper says there is a prior on the gap width of more than 20 solar masses.
Yeah, it's the same if you take it down to 0. We did that in response to the referee. And the notch filter allows there to be a complete, like a non-empty gap, and the max likelihood is empty gap. But of course, you can't measure a rate of 0. It's just like, ultimately, it's just an upper limit. So yeah, I think it's the same thing. Actual question is, why did the common envelope channel come back?
Okay, yes. So I want to remind people that Monica's paper in 2021 was not a population synthesis. It was slices of MESA runs at one metallicity. Maybe we had inserted a second metallicity, and we said in the paper, based on these results, it looks like if the population is dominated by 0.1 solar metallicity, that it would for that particular case, the common envelope channel was killed. But now we're doing full population synthesis with cosmology, with a full star formation rate again, across metallicities and redshift. And we have ratios of the two channels as a function of redshift, and depending on the cosmological star formation rate, you get a crossing of the two models. And when you look at the mass distribution, there are models where the two channels are comparable. There are models where one dominates over the other. And yeah, that's how it came back.
Come back in lower or higher metallicity?
I'm sorry, what?
Coming back at lower or higher metallicity?
We're still mining the data, so can I get back to you on this? I couldn't tell you.
Hi, thanks. Can you talk a bit about what sort of biases might be possible when trying to interpret non-parametric models, and if there are any biases that may be possible?
Okay, I'll give you an example. Yeah, actually, there's a striking example in our own work. Here, low masses. Is it this one? Let me remember. Yeah, I believe it's this one. Sorry. Even better, bigger plot. Low mass ratio distribution. It has a peak. But many analyses, including the Anaria and Kalogera paper that's out on the archive, these results are not. We assume the mass ratio is a single power law. If you assume the mass ratio distribution is a single power law, you are not going to find a peak at 0.6. What it will do, the model struggles, but what it will do is it's going to give you railing to 1 with huge error bars. That's what a prescriptive model does. And you can look at the results of that paper, which came out, what was it, 2 months ago, where we wanted to do something different, but it was not non-parametric. We stuck a power law in, it doesn't pick up the peak. But it cannot. You made it a power law. No, we made it a power law.
Thanks, Vicky. Aditya Vijayakumar, CETA. So two very quick clarifications. One, the LVK paper is still not published in AppJ Letters. It's still under review. And I saw on your title that you had said AppJ Letters, so I just wanted to clarify that.
Oh, okay.
Yeah.
All right. Sorry.
The second thing is we also, I just wanted to also clarify that in that mass distribution plot, there is a non-parametric model, which is this Godfrey et al. Splines model.
Okay. Sorry.
But
yeah, the B-spline, yes, it is, yes, I would say the Bin-Gaussian process is as non-parametric as it gets, and you get the biggest error bars, and it's the worst. Yeah. And if you see a peak even in the worst, yes, the peak is real. That's all I'm saying.
I think I might agree with that. Well, but my actual scientific question is, you made a claim that at the less than 30 solar mass spin, there's at least dominant is not dynamical. But I'm a bit confused by that. If the natal spins of black holes in both dynamical and isolated formation channels is around 0, then you'd see a chi-effective of 0, right? So
I'm sorry, I didn't get it.
So if the natal spins,
yes,
say you're talking about 1G black hole mergers from the dynamical channels and yes, then the isolated formation channel, both of those, the natal spins are 0, yes, then you'd also see a chi-effective that peaks near 0. So just seeing yes, that chi-effectives peak near 0 does not really, or not very large values
correct.
is not.
So we're not basing it on chi-effective primarily. Let me get it where all here. So are you talking about the low masses?
Yes, the first column.
Yeah. So we're mainly basing it on this. The cluster models, they're all railing at 1, and it's not just these 4.
Okay,
they're all
okay,
railing
fine.
at 1.
Okay, maybe I misunderstood.
The dynamics models are railing at 1 for 1G, which is the dominant rate. So it's the difference between the chi effective here, is it really at 0? Is it to the right of 0? If it were only that.
Hi. So, Carl Rodriguez, UNC. I just wanted to, I guess, speculate on something, which is that even in the isolated channels, right, those should all happen in clusters as well, right? I presume that most clusters start off with binaries. Common envelope, as an example, has a very short delay time. And so I'm going to form a compact binary that probably won't interact and merge in the cluster. And so even if and so it seems to me, and I'd just love to hear your thoughts on this, that anything that is present, even in the isolated channels, should be duplicated at some level in the 1G plus 2G population.
I don't agree.
Okay.
Let me explain. It depends. So, I mean, the bulk of the binary black holes, and you're the cluster modeler, but my understanding is that the bulk of binary black holes out of clusters, they're coming from the Spitzer instability, where black holes ended up single, they went all the way into the center, and that's where you're forming them. None of this happens in isolated binaries. The only thing where you might have this overlap between the field and the cluster is the beginnings, where the initial conditions, what we call initial conditions in the field, may actually have been affected if everything gets formed in clusters. Initially, your initial conditions from star formation can get affected from the early dynamics, because the binaries have cross-section, they're interacting. That has been shown in young clusters, right? You start with initial conditions, you put them in a cluster, depending on the conditions of the cluster, in 10 million years, a few million years, you can change their orbits. That's the only, but you're not going to get the real dynamics process.
No, but that's not what I mean. I was getting at common envelope, right? That occurs within a few mega years, right, for massive stars, right? And so that's going to happen. I'm going to have some population of isolated binaries in every cluster, right? If it was a stable mass transfer and they lived for 500 million, or they expanded their orbits, then dynamics would mess with them. But if the common envelope is back, it's somehow returned, then I can get some population of 1G plus 1G from isolated, that evolve as isolated binaries in the cluster. Their merger products stay in the cluster. I guess what I'm trying to say is it seems to me that everything in the 1G population, even those from isolated binaries, should be copied at some point, even at a very low level in the 2G population.
But in the cluster simulation, you know how many of your binary black holes came from the original primordial.
Oh yeah, it's minuscule, but it's not zero.
It's minuscule, yeah. But it wouldn't affect these features.
Sure.
The rate is nothing. Okay. The relative rate.
Hi, Lieke van Son, Radboud University here. Beautiful plots. Vicky, I really love to see you and everyone and Monica exploring the 9 solar mass peak in Poseidon. I have lots of questions, so I can only ask a few. And I want to ask about the stable mass transfer common envelope mass ratio distributions in particular, because you showed a plot where you have like many different lines for the common envelope and stable mass transfer mass ratios.
Yes.
Yeah.
Next slide.
And
here.
Yes, this one. And I want to say I'm not too surprised that the common envelope channel is back, as Maya said it. I don't think it was ever away. I just ignored it. But what I find, at least, or what I understand about the stable mass transfer channel is why it would lead to a peak in the mass ratio that peaks away at one.
And then you can ask, why does the common envelope?
Exactly. So I was actually wondering if that plot at the bottom, if the extreme mass ratio lines, do those, no, the ones on the left, that plot, sorry, no, the other plot. No, but you had the right plot, but different lines. Exactly, those. Yes. Are those all common envelope mass ratio distributions?
Yeah, so if, I don't know. So, but we can, I'm happy to sort of dive in.
Yeah.
Because these plots were made yesterday after our session when I told Monica, can you plot this thing for as many models as you can dive in? So it's possible.
Okay, we should talk more, but I get, my hope is That even between the stable mass transfer and the common envelope channel, we will be able to distinguish based on the mass
potentially. Maybe not for all models, because here, for example, when it comes to this parameter, the peaks are together, but you know, one is much broader, etc. So there will be differences. I agree. You're right.
I think I saw 5 hands, but yeah, we are out of time. So we have time for one question. So I don't know who wants to.
I saw Ilya has a question.
Yeah, we
really
fought
want to
over
hear
it.
Ilya.
We fought over it.
Selma, you haven't asked, so go ahead.
I came in this conference thinking that there was 2 features we were certain about, the 9 solar mass peak and the 30 solar mass peak. And so in the openings plot, can you show that again?
The which plot?
At the opening,
yes.
the one you didn't find here, on the
here.
left.
Yes.
Yeah. So I definitely see something between 20 and 35, but that's very different than the bump at 30 to me.
Yeah, so you don't see a real 30, so actually I had the lines, no, it's the previous one.
So is the 30 solar mass crisis?
Here's the width of the 35 peak, which is 29 to 36 by the analysis of the collaboration. I am not claiming that now the 35 peak, because the non-parametric analysis makes it so broad, that this is where it is. Because the non-parametric analysis will always give you bigger error bars, okay? So it makes it much broader. It doesn't mean it is much broader. But what the collaboration is finding with a B-spline, which is very weakly parametric, it is a peak. The B-spline is the blue. So this is even weakly, you know, it's really crazy non-parametric, so it is consistent with the result. It doesn't contradict it. It just makes it broader. Does that answer your question? Yeah.
Okay. So I'm really sorry to those who I could not get to, but I think Vicky is here like till tomorrow.
Yeah, I'll be here the whole night answering questions.
So please find Vicky.
I'm flying tomorrow.
I think we should thank Vicky again. And since
would like to thank the organizers. I hope somebody does it. But
yeah. So.